Hello, everyone, and welcome back. In this lecture, we're going to continue our suite of lectures where we're talking about finding the volume of shapes in 3 dimensions. You'll remember that in the previous lecture, we introduced this method of cross sections, which eventually led us to a Riemann sum, which would converge under appropriate conditions to a definite integral. In this lecture, we're going to take another approach that allows us to first define shapes in 3 dimensions and then find the volume of those shapes. So let's jump right in. We're going to be interested in what are called surfaces of revolution. So that might be where you're given some sort of abstract shape and you're asked to rotate that shape around an axis. And you can imagine that as you rotate this thing around some axis, it fills out a volume in 3 dimensions. You can think of this as sort of vapor trails that are forming a solid here. And what's really, really cool is that this is used in computer graphics all the time. A few years ago, I had the pleasure of going to a Pixar exhibit at a science and tech museum, and they showed that the scream canisters from Monsters, Inc. were built in exactly this way. They basically made a 2-dimensional cross section of each one of these cylinders, and then used this surface of revolution method to sweep it around to get these perfectly symmetrical and cylindrical looking scream canisters. So today we're going to talk about how we can actually do this. Let me start with a specific idea here. So imagine I give you some function. It always starts with functions and it always ends with definite integrals. I give you a function and I give you bounds as usual. So this is A, this is B, this is my 2-dimensional area. And what I would like to do is I would like to rotate that thing around. And so this thing is specifically, we'll just call this function f of x for now. So this will fill out our function. And the question is, how do we compute the area or the volume of this thing? Well, if we take the approach that we had in the previous lecture, we find these cross-sectional areas. So first thing first, what are the cross-sectional areas? Well, when you take a slice of this thing, because you rotated it, every single slice is a perfect circle. That's just coming from the fact that you rotated it. And so then we know the area of a circle. This tells us that the area of a cross section is given by pi times the radius of that cross section squared. So the question is, what is the radius? Well, abstractly, we can just say this might be some function that depends on where we are in x. But in the specific case of my little picture here, what would the radius be? Well, the radius for a value of x would be the distance from the center of this object. So in my case, the axis of revolution, this is my x-axis here, and out all the way to the edge of the object. So in this case, it would be out all the way to the edge of the object defined by the curve that I'm rotating around. So in my case, the radius here, the radius is equal to the value of my function f of x. What this tells you, now that I have the area of the cross sections, I can go back to what we talked about in the previous lecture. I can say the volume of this object, this thing is equal to the integral over the bounds on A of each one of these cross-sectional areas. or this general function for the cross-sectional areas. So it's one thing to give you this very, very abstract way of thinking about this. Let me actually just do some examples so that you can really see this at work. So let's start with the first example here. Let's talk about the region that's going to be between the curve y equal to the square root of x, where x is going to be between 0 and 4. So that makes up our a and b values. And the x-axis, sorry. And this is going to be to generate a solid. Find its volume. So the same problem from the previous lecture. Really now we just need to find its radius. So let's give this a little sketch. We know that my sketches aren't too pretty, but hopefully they still help us a little bit. My function is the square root of x. And this is going to be between 0 and 4. So here's 4, here's 0. Here's my area. This is basically the same idea as the little sketch that I started with up here, because as you can see, in this case, the radius, again, is just given by the value of the function. So this tells me that the volume is equal to the definite integral from 0 to 4 of each, and then the function for the cross-sectional area, a of x, which is going to be pi r squared. So pi times r of x squared dx, which is equal to, the radius in this case is the value of the function, so square root of x. I'm squaring that thing. So I'm really just integrating x. So pi times x dx. This leaves me with pi x squared over 2 running from 0 to 4. And in this case, we get a volume of 8 pi. So that's great, right? Now we have a way of not only calculating the volume from the previous lecture, but also we can generate these shapes. So this is kind of fun. We can play with a lot of cool ideas and techniques here. Let me give you another fun example. We can use this method to derive known equations. So for example, let's consider the circle given by x squared plus y squared is equal to a squared. And we're going to imagine that it's rotated around the x-axis to generate a sphere. Find its volume. Right, so this is a classic formula that we're probably familiar with, right? We were presented with this formula maybe in grade school that told us that the volume of a sphere is given by 4 over 3 pi times the radius cubed. Now, we're going to actually derive this using this method of surfaces of revolution. In this case, the radius of this sphere and of this circle is going to be given by this value a, right? So this is going to take on our radius. And so the answer that we should be coming up with is 4 over 3 pi a cubed, because we know this from grade school, maybe. So let me start with a little sketch first. So here's my circle. Here's the X and Y axes. And we're being asked to rotate this thing around the X axis. So the question is, what is the cross-sectional area at each point, at each value of X? So if I pick this value of X right here, what is the cross-sectional area? So every single slice of this thing, again, is going to be a circle that's coming from the surface of revolution that we're forming. And so you can see that the radius of each one of these things is going to be given by the Y value here. So that tells me that the cross-sectional area as a function of X is going to be given by pi y squared. Now, if I flip back for a second, I know that the circle itself is given by the formula x squared plus y squared is equal to a squared. So I can rearrange that and isolate for y squared. So let's flip back over. And I know that this is given by a squared minus x squared. So now I just have a function of x. It gives me the exact area for each one of these cross sections. And so therefore, the volume is going to be given by, we'll talk about the bounds in a moment, a of x dx. So the question is, what are the bounds? We are running from here to here on this circle. In this case, y is equal to 0. You can use that expression x squared plus y squared is equal to a squared to find out what these left and right extremities are. They're given by a comma 0 and minus a comma 0, meaning that x is running from minus a all the way up to plus a. So we can fill in what we know. We get minus a to a pi a squared minus x squared dx. Don't get intimidated by the Greek letter pi in here, right? That's just a number, 3.1415, blah, blah, blah. A is just a constant, right? So it's not affecting the integration here. This is just a constant function. The only thing that we're integrating with respect to is x. So this means that I get pi a squared x, because that was pi a squared. It was a constant function, minus pi x cubed over 3. And this is running from minus a to a. And now when you do that, when you plug this in, when you evaluate this, you're going to get exactly our formula, 4 over 3 pi a cubed. And this is kind of cool, right? This is a pattern you see all throughout geometry, maybe when you learn these things for the first time. But typically, two-dimensional shapes, the powers on these things are squared, right? A length times width or a radius squared, whereas a volume comes from a cubic power, right? So the length times width times height, maybe, or the radius cubed. Well, one way you might have been introduced to some motivations for this, but the real reason is because it's integration, right? Each step, you're adding another power because you're sort of going up this chain when you're doing these integration schemes, right? You're taking a squared function and moving it up to a cubic function. Okay, maybe you're not too impressed, right? Let me give you another example. Hopefully I can win you back and really impress you here. So let's do a third example. So find the volume of the solid generated by rotating or by revolving the region bounded by y equal to the square root of x, and the lines y equal to 1, x equal to 4, about y is equal to 1. Okay, so this is a little trickier, right? In the previous examples, we were revolving about y equal to 0, the x-axis. But that's fine. We can still do this. Let's start by taking or by sketching out what exactly the region looks like so we can calculate this, this radius that we need. So let me sketch my function. This is y equal to the square root of x. And in this case, the region is bounded by y equal to 1 and x equal to 4. And this region right in here is what's going to be revolved. And it's going to be revolved around y equal to 1. So the question is, what is the radius of this object? Well, since we're revolving around y equal to 1, that's representing the center of this thing. And the radius is coming up and out until it touches the curve y equal to the square root of x. And so that tells us that the radius as a function of x is going to be the square root of x all the way out to the red curve minus 1. Because if it was just the square root of x, that would be measuring the distance from the x-axis way down here all the way up to the square root of x. But in our case, we're starting at y equal to 1, so we want to break off this negative space right down here. So that tells us that our area function is equal to pi and then the square root of x minus 1 all squared. Let's expand that out, make our lives a little easier. So x minus 2 root x plus 1. And so now we've boiled it down to a definite integral problem. So let's do the volume. I'll put in the bounds in a moment. X, so here's our radius squared function. The question is, what are we integrating to and from? Well, we can see we're going all the way up to 4, so that's okay. The question is, we're starting right here. What is this point? Well, this point represents the intersection between y equal to 1 and root x equal to 1. So you can solve this algebraically, and this is going to give you the point 1, 1. So that means that the x value that we're starting at is equal to 1. And so here now, this integration again is fairly straightforward. It's something that we've been doing over and over and over again. So I get pi, and then I'll do all the integrations. So x squared over 2, that's integrating x, minus 2 times 2/3 x to the 3 over 2. That's a function we've seen a lot lately. And then integrating 1 gives us x. And this is running from 1 to 4, which I'll leave you to plug in the bounds here. But this gives me 7 pi over 6. Okay, maybe you're not as impressed as I think that you should be. I certainly think this is pretty cool, but you can do this in different ways. You can actually rotate around different axes if you want, right? Nothing says that it has to be rotated in this sort of horizontal direction. We could instead rotate around the vertical direction. So for example, I could rotate a function around the y-axis. The only thing that's going to change here is that the integral will be posed in terms of y instead of in terms of x. This is similar to what we did with bounding or calculating the area bounded between two curves, right? Remember the last example, we said you can either do it in this sort of complex way where you have to do it piecewise in X, or you can do it in a relatively straightforward way by doing it in Y instead. So let me give you an example where we can use integration in Y. Example number 4. So let's say find the volume of the solid generated by revolving the region between the y-axis and the curve x is equal to 2 over y. So I'm going to give this to you as a function x as a function of y, because we're going to be integrating with respect to y. But that's fine. You can multiply both sides by y, divide both sides by x. You can get y is equal to 2 over x. It's the same function here. And 1 is less than or equal to y, which is less than or equal to 4. And this is going to be rotated about the y-axis. So this is rotated about a vertical axis instead of the previous cases where we rotated about a horizontal axis. So same as always, we've got to start with a sketch. So here, the function is given by x equal to 2 over y, or that's the same as y is equal to x over 2, or sorry, 2 over x. So you've got that singularity at 0, and this is x is equal to 2 over y. In this case, we're going between y is equal to 1 and y is equal to 4. So let's say here is 1. Let's say way up here is 4. This gives me this region right in here. And I am asked to rotate this thing about the y-axis. So we essentially have exactly the same problem, right? We have to ask ourselves, what is the radius of this thing, right? If you remember from the previous video, it didn't matter sort of how we orient these things in space. You just need to take your cross sections appropriately. So in my case, I'm taking cross sections which are perpendicular to the vertical axis, as opposed to the previous case where we took them perpendicular to the horizontal axis. So that means that my radius, if I can draw over this in another color, is given by this distance right here. So the distance from the y-axis out to the function. So the question is, what is my radius? Well, r of x, in this case, goes from x equal to 0 all the way out to x is equal to 2 over y. So it's exactly the same as the first example we did here. The only thing that changed is that I put things in terms of y instead of in terms of x. So my radius is 2 over y now. And so my volume is going to be pi times my radius squared. Now I'm integrating with respect to y. And my bounds of integration are going from 1 all the way up to 4. That was given to me in the problem. So let's expand this out, make it look a little prettier. Let's put the 4 out front and say this is, let's write it as y to the minus 2. I think it's a little nicer to keep it all on one line. And then the integration is a little easier too, because you're just sort of adding 1 to the exponent. So this gives me 4 pi times minus 1 over y, the antiderivative of y to the minus 2. So this is minus 1 y to the minus 1, however you want to write it. I realize that I sort of jump back and forth between notation there. And this gives me 4 pi times 3/4, which gives me a volume of 3 pi. Okay, so through these examples, we've seen, first of all, we can create shapes by doing these solids, or by creating these solids of revolution, right? So you give me a two-dimensional region, I rotate that thing around some axis, and now, boom, we've got a three-dimensional shape. What we can do with this not only is compute or build these shapes, we can also compute their volumes using that method of cross sections. And the beautiful part about this is that the cross sections are much easier because they're always circles, coming from the fact that we're rotating this thing in a perfectly circular manner. So we're going to extend this discussion in the lecture that follows. So please move on to that when you're finished.